Hi, everyone. One, two, three, four, five. PGO is fine. Yep. We are all Rust engineers. We love performance. We use Rust for performance, so on. And for today, we are going to talk about one specific compiler optimization that is useful for actually any kind of CPU-intensive part of your application. Not only Rust, but we are at Rust conference anyway. And this optimization is called Profile Guide Optimization, or PGO. Before we start, I want to show you some benchmarks. Most of them are done by my hands for different applications and libraries. Some of them are, most of them regarding libraries are written in Rust, regarding applications. Not all of them, but I'm almost sure that you know and use on a daily basis many of them. And all of these results and performance speed up I got, and not only me, only by applying PGO to an application. Databases, parsers, compilers, libraries in different domains, game engines, and so on, all of them can be optimized with PGO. It's not a theoretical thing. The benchmarks were not synthetic. They are on nearly real workload. For example, for databases, it's were OLAP workloads for analytical stuff. And at least I hope they're encouraged enough. Few words about me. Actually, I am not a Rust engineer. I am from a C++ camp. I was using C++, I guess, almost 15 years. And several years ago, I decided to switch to Rust because, you know, I donated my hair to C++ chaotic gods. Yep. And from C++ perspective, I was working with ISO Working Group 21, which is also known as C++ Normalization Committee. If you know something about C++, I was working on compile computation stuff and some numerics like const export things and so on. By the way, C++ is better in compile time computation compared to Rust, at least for now. I spent several years on hacking LLVM from different perspectives. My field of interest are hardware-independent optimizations, which is PGO is, and hacking different stuff like lib C++, static analysis, and so on. Not professionally, just for lulz, but anyway, I know something. And spent last year and a half with PGO on almost daily basis, so at least I gathered some experience with this technology and what I want to share with you for now. And actually, when I was leaving C++, I decided not to switching to Rust professionally and decided just to stop coding. So, like for now, just confidence and draw your engineer, nothing so interesting to share. So let's start. Actually, there are two schools how or camps how our application can be compiled. The first one is the most common for us, as for Rust, ahead of time school. We have our source code, which is compiled by a compiler, and the generated binary is deployed to a target machine where it's running. The second camp is just-in-time compilation model. We're not talking about interpreter things, interpreters, something like that. We don't care at all about Python at all. We have completely almost the same thing, but at least the compiler generates some kind of bytecode, and this bytecode is deployed to a target machine. And on a target machine, it's compiled just in time during the execution to a machine code. This model, just-in-time model, has one intrinsic advantage over AOT. Because modern compilers, good compilers optimizations do a lot of interesting stuff. Inlining, loop roll-unrolling, hot-cold code splitting, even LTO, if your compiler is good enough, and many other things. We will not talk about all of them in details. We need to understand that all of these optimizations can benefit a lot from providing runtime information about how our application is executed, which parts of applications are executed, how frequently, and so on. If in just-in-time case, we can collect all these metrics on a target machine because we have a compiler or interpreter on a target machine. In AOT world, we cannot do it because we don't have a compiler. And Actually, modern compiler has some kind of implicit performance model for your application about for example, LLVM has a lot of internal constants like inlining thresholds, loop roll and rolling thresholds, and so on. They are simply written into the sources, and they are good enough for generic case, but unfortunately, modern applications are different applications for different domains, and these constants are not the best in every situation. And it's where the profile guide optimization comes in. The solution is pretty simple. Let's try to collect runtime statistics about how our application is executed. This statistics is called PGO profile. Pass the profile to a compiler and use this profile during the compilation phase. And that's it. That's all the idea. For example, let's check one simple function in Rust. Let's compare it. An input int variable is some numbers and so on. And in the middle, you'll see assembly that is compiled in the release mode, opt level 3, nothing else. So nothing too interesting except that the second and the third branch are swapped for some reason by the Rustc compiler. I don't know why, because for the same code, but with Clang, of course, for C++ version, they are not swapped. But anyway, it doesn't matter in that case. Here we have completely the same. We have the assembly completely for the same function, but after applying the profile guide optimization. The training workload, the typical workload in this case, were passing values, where the most frequent value as an input were 322. And the compiler decided to optimize the function a little bit in our case, in our way. The first big difference that the most frequent branch was moved to the beginning of the function is a simple idea, because we can achieve an early return, and less of the redundant functions will be executed in runtime, and we will get a better performance. The second change is moving the return statement to the beginning of the function, because return statement will be executed with the second branch, and we will get a better CPU instruction cache usage. And the rest of the function is not changed. They just moved to the back of the assembly. And that's it. Actually, there are different kinds of PGO. The most common one is instrumentation PGO. It's a default one. It's available in many compilers. And if someone decides to implement a PGO, they probably will start from instrumentation. Sampling PGO is another approach. We will talk about all of them a bit later. And actually, these two are the most common one. And actually, there are a bunch another of kinds of PGO, like context-sensitive intermediate representation PGO, temporal PGO, and so on. Unfortunately, they, for now, available only for C++ world, not for Rust yet. So let's start from the most basic one. How does instrumentation PGO work? You need to compile your application in instrumentation mode, run the instrumented binary on your typical workload, like a training phase, like a machine learning training if you want, collect PGO profiles, and you need to recompile your application once again with this information. And that's it. What does it mean, instrumentation in practice? Once again, a simple function that we compare an input variable with the meaning of life, and in the middle we see release assembly for a simple opt level 3 mode, compilation mode. On the right side, we also compile our function in the release mode, but with enabled instrumentation. The first difference we see an additional instruction. It's a counter that is automatically inserted by a compiler during the instrumentation phase, and each time when the function is executed, this counter is incremented. And then, at the exit of your program, all these counters are automatically saved to a disk, to a file, default.profro. Of course, the file name can be changed, and so on. And that's it. Also, you will see here LLVM profile raw version, because it's a file. File has a format, and the format has some versioning stuff. For example, if you will generate PGO profile with one compiler version, it will try to process it with another compiler version. With high probability, you will get something like LVM error, PGO profile are not compatible, I give up, I cannot process it. And that's it. Unfortunately, instrumentation PGO has a lot of caveats. At first, you need to compile your application at least twice, during the instrumentation phase and during the optimization phase. And if your program is huge enough, your CI pipeline will not be happy, trust me. An instrumented binary is larger because additional amount of instructions is inserted to your application. And instrumented binary is slower because an additional amount of instruction is executed during the runtime. But how critical these caveats are in practice? Let's start from the binary size increase. I collected some numbers. I have a lot more of them. I will show them a bit later. Actually, we don't see anything critical here for applications like database and so on because we are not space limited nowadays. However, it can be critical for you if you are working like in the embedded domain and so on. So please be careful. But the worst thing are here things. Binary slowdown. Actually, in practice, it cannot be really predictable. For example, let's check the ClickHouse case. It's not a mistake. The actual slowdown during my benchmarks was really more than 300 times. It's because the PGO counters were inserted to a really hot loops inside ClickHouse, and they were executed really frequently. That's why the performance penalty is so high here. For our applications, the actual slowdown can be more or less. It depends on the application. It depends on your typical workload and so on. Google is the largest PGO user in the world, as far as I know. Met such problems something like, I guess, 15 years ago, and they decided to implement another PGO way that is called sampling PGO. How does sampling PGO work? The biggest difference is that you don't have an instrumentation phase. You run your usual typical application that is compiled in the release mode almost without additional flags. Instead of collecting information about how your application is executed via built-in counters into your binary, we are trying to attach some external things like a Linux perf profiler or Intel vTune, whatever you want, or anything else. Collect some stack traces and so on. Then you need to recompile your application once again with this runtime information, and the rest is the same, profit. That's it. Unfortunately, sampling PGO also has caveats. The first one is a specific hardware feature that is called branch stack sampling, or BSS. This hardware feature helps to your profiler collect stack frames in a more efficient way. Unfortunately, availability of this feature in the hardware and operating system combination can be a bit tricky. Intel CPUs are on the good side. This feature is called for Intel Last Branch Record, or LBR, and it's available since Nehalem CPU, and the support to the Linux kernel was added many years ago. Sorry, this technology, as far as I know, is not available for our operating systems like Windows or Mac OS. Actually, I don't care much about them, sorry. Regarding AMD platform, this feature is called branch sampling, or BRS, and it's available since Zen 3 CPUs, Zen 3 only for server side, Zen 4 for all CPUs. And the support into the Linux kernel was added like 2 years ago. If we're talking about ARM, this feature is called BRBE, Branch Record Buffer Extension, and it's available only from the, as far as I know, the most recent ARM specification, and I'm not sure that the feature is currently in upstream to the most recent Linux kernel. Also, Android platform uses another set of ARM features that are called core side. Honestly, I cannot say much about Android stuff and how they use it in practice. RISC-V, this feature is called Control Transfer Records, or CTR. Current status, work in progress, nothing to try yet. And actually, there are a bunch of other platforms like mainframes, AIX, PowerPC, and so on, you need to check it on your own. And the biggest limitation with sampling PGO that, as far as I know, modern hypervisors don't emulate this feature in CPU. So if you have virtual machine, you cannot use it. This hardware feature, unfortunately. It could be a limitation, but anyway, you can try to gather PGO profiles from a bare metal. Also, sampling PGO, unfortunately, has a very limited tooling support compared to instrumentation PGO. Google invented sampling PGO, and they implemented some amount of tooling around it that is called Google Auto-PGO. Actually, that is the reason why sampling PGO often is called FDO, feedback-driven optimization. That's because of this name of this project. Unfortunately, Google Auto-FDO buggy as hell. It has a lot of compilation issues with the most recent LLVM versions. You need to patch it. Google engineers don't care much about the outside of the Google, so they don't care. So that's it. That's the current situation. Fortunately, there is another tool that is called LLVM ProfGen. It's already upstream to LLVM, so at least it doesn't have compilation issues because of monorepository, you know. Unfortunately, this tool works only with sampling PGO profile with BSS feature enabled. Google Auto-FDO can work with sampling PGO profile without BSS. Yes, they will be less efficient, but anyway, it will work. So let's compare instrumentation versus sampling. At first, instrumentation allows to achieve better optimization. Once again, according to Google, sampling PGO has from 80 to 90% of efficiency compared to instrumentation PGO. Sampling has far, far less runtime overhead. That's why it was implemented, something like 2% of runtime overhead compared to plus infinity with instrumentation. Remember the ClickHouse case. And even this amount of overhead can be tweaked via the sampling rate of your profiler. So if you want to get more precise profile and you are fine enough if more performance penalty, just increase sampling frequency. Want to reduce performance penalty, decrease sampling frequency, that's it. And instrumentation, once again, has better OS and tooling support because it's a default PGO mode. So let's discuss about the most common PGO traps and mitigations for them. The most common one that PGO optimizes one cases and optimizes another cases. That's how it works. It can be critical for you because you don't want to pessimize some workloads. You can try to build different versions of your applications per workload. For example, like several web servers and route the traffic between them on some proxy on Nginx, and that's it. If it's not possible, you can try to gather multiple PGO profiles from multiple workloads and merge them via a tooling like LLVM ProfData. Also, it's available as a part of LLVM. Probably you will not get a peak performance per specific workload, but anyway, the performance boost is expected. PGO build is not reproducible. Reproducibility is a hot topic nowadays because of security and blah, blah, blah. And you know, PGO can make things a bit worse because it's an additional input, a PGO profile. Good thing is that you can just collect a PGO profile and commit it to a version control system. And each time when you will use the same PGO profile, the build will be the same. There is another topic about gathering PGO profile in a reproducible way, but it's out of the topic. But I will discuss after the talk. I will be happy to do it. But if you save PGO profile to a VCS, you will get another problem that is called profile skew problem. What is it? When you save a PGO profile, your application is not static. Some code is changed, new code is added, and so on, and this new code is not covered by your gathered runtime statistics. And so it will not be PGO optimized. How to resolve it? Just regenerate PGO profiles with some frequency. Each commit, each week, each month, whatever you want. It depends on multiple variables like frequency of how your code is changed and so on. You need to implement the PGO regeneration strategy on your own. And the most interesting one, unfortunately, PGO is not a silver bullet, and it cannot optimize some applications, especially if they are already heavily optimized, like codecs, a lot of inline assembly, and so on. So congratulations that you find such a piece of good software, actually, but you know, the situation can change in a few months or so if when new code will be added to a project, so probably it will be less optimized and so on, and for such places, PGO can help you in the future. So if it doesn't work for you now, give it a try in a few months or so. So how should I collect PGO profiles? Actually, there are different strategies for that, but the first one, please don't collect PGO profiles from unit tests. The main aim of unit tests is testing your application in all cases. Most of them are corner cases. I hope you are not going to optimize your application to corner cases. You want to optimize them to a real workload, so please don't unit test. However, if your unit tests represent a real workload, go ahead, but that probably are not good enough unit tests. From benchmarks, it depends. It depends on how similar these benchmarks are to your real workload. If they are similar, go ahead with benchmarks, you are fine. If they are not, be careful. Manually crafted training scenario, actually, it's a good option. For example, the Rustc compiler. Rustc is already PGO optimized, and if you use Rustc compiler from the main distribution, you get the fastest version of the Rustc. And the Rustc compiler uses completely this way. What is it? You can just write a bash script or something like that, and run and type your typical workload. For example, for a compiler, the typical workload is compiling. So Rustc just compiles in the instrumentation mode. The Rustc compiler compiles a simple program with an instrumented version of Rustc, collect PGO profiles, and then recompiles it once again. That's it. Actually, that's a good option, but don't forget to track that your manually crafted training scenario is not very different from your target workload. For example, if you have a very dynamic target workload, probably this option is not the best one. And actually, you can gather PGO profiles directly from production. That's why sampling PGO was implemented, and that's how Google uses it inside. It's actually one of the best options, but unfortunately, if you are going with this one, probably instrumentation PGO is not your best friend, and you need to start with a sampling PGO. Unfortunately, there is not a silver bullet. Once again, it depends. So, what about Rust? PGO support in the Rust compilers. At first, the most common one compiler, the Rustc compiler, supports both instrumentation and sampling PGO. Unfortunately, sampling PGO is not documented, but anyway. Good news that same for the Rustc compiler, because it's the downstream for the Rustc. Bad news that Rustc compiler doesn't support the most advanced PGO types like a temporal, context-sensitive things, and so on. And even if they are implemented in LLVM and in the Clang compiler, because Google contributes mostly to Clang, not to the Rustc, and Facebook too. Facebook also uses PGO a lot inside. GCC arrays, if you care about GCC ecosystem for Rust, unfortunately no support for PGO yet, and they don't care about it, at least for now. They have another priorities. mRustc, if you care about no support, and if there are other compilers, I actually don't know, but I'm pretty sure they don't support PGO too. What about PGO issues in the Rustc compiler? At first, documentation. Unfortunately, documentation is too bad compared to the Clang one. And actually, the Rustc documentation about PGO has a link to the Clang documentation. So if you want to read about PGO in details, it will be the better strategy just start with Clang documentation. So there is an open issue to improve the documentation, but it's still open, and no one really cares in the upstream. Missing most advanced PGO modes, like temporal and so on. There are some nasty bugs. For example, there is a bug in the Rustc compiler when you cannot, for some projects, due to some yet unknown LLVM bug, you cannot enable LTO, link time optimization, and PGO at the same time. No one knows what is going on there. I've reported like more than 10 projects if there's the same bug, but unfortunately it's not fixed yet. I need to check my counter. Oh, OK. And WebAssembly target is not supported yet due to some LLVM limitation. This one will be resolved this year, I hope so. And multilingual PGO pipelines can be a bit of pain. For example, if you have a Rustc core, Rustc application, if you have some C++ dependency, and you want to optimize PGO, if PGO is a whole application, you need to recompile and C++ and Rust, and you need to pass all required flags to both compilers. It can be a bit of pain. I did it multiple times, trust me. So what about other languages? C++ has the best support in the world because of Google. D and other GCC LLVM-based compilers almost the same as C++ and Rust, but without most advanced features. The Go compiler was added only sampling PGO support last year in August. So supports, but can do a little for now. C# supports. I cannot say much because, fortunately, I'm not a C# engineer. And for Java ecosystem, there is an AOT compiler. It is called GraalVM. Unfortunately, supports, but not enough publicly available information. At some point, they stopped answering my questions in the upstream. And other languages compilers, if high probability, PGO will not be supported. What about ecosystem for PGO in Rust? There is a tool that is called Cargo PGO. The tool is written the PGO got in the Rust ecosystem, Jakub Biranek, aka Kobzol. This guy optimized the Rustc compiler with PGO and other more advanced techniques. This tool is available here, and with this tool, you can optimize your Rust application in this way. That's it. And that's how I optimized many of Rust applications and gathered a lot of benchmarks, exactly in this way. It also can use benchmark and so on. It also supports more advanced optimizations like post-link time and so on. Please start with it. What about current PGO states across Rust applications? Almost no applications support building with PGO, and they build scripts. Whereas the distributions also don't build its software with PGO because there is no support in the upstream, and they don't care much about tweaking build scripts and so on. However, some OS distributions enable PGO with more frequently, like Gentoo, Clear Linux, or Cache OS. So if you want to find some inspiration, take a look on them. So rule of thumb, if you want to get PGO for your application, just recompile it on yourself. Some pretty familiar examples from our sponsors and presenters. So that's the current state of our ecosystem. So that's it. So no comments. What about good candidates for applying PGO on? Actually, any CPU-intensive applications with many branches inside, like compilers, interpreters, databases, a lot of parsers like XML, JSON, protobuf, whatever. I've seen a lot of mentions of Server library. It can be optimized a lot, as you've seen on the second slide. Operating systems, Oxidize, for example. And many of them can be optimized, so please do it if you want to be blazing fast. If you want to simple optimization roadmap, at first, release Motop level 3. Please enable LTO, because it will be easier. Not all software for now uses LTO, unfortunately. Then probably CodeGen units 1. Only after that, try to enable PGO. and probably instrumentation by default, sampling in the most advanced case, like running, gathering PGO profiles in production, and more advanced techniques. More advanced techniques like continuous PGO mode, that's the way how Google collects PGO profiles for all their services. They have a dedicated project inside, unfortunately closed source. There are ideas to implement it based on open source projects like Grafana, Pyroscope, and the Elastic Universal Profiling Platform. Unfortunately, only discussions for now. There are tools like post-link optimizations, LLVM Bolt, Google Propeller, or Intel Thin Layout Optimizer that can optimize your software even after applying PGO. The Rustc compiler is already optimized with LLVM Bolt, fortunately. You can apply PGO to the operating system and tweak operating system to run one specific workload, for example, databases, because they have specific pattern specific patterns, workload patterns. Applying machine learning stuff, LLVM has already some kind of integration of machine learning infrastructure, and so on, and many, many other things. I don't have time today, maybe next time. And that's it for today. Actually, if you are interested enough in PGO, I highly recommend the best source in the internet about PGO. It's my repository about awesome PGO. It has many, many, many benchmarks materials about the current state of PGO across multiple ecosystems, not only Rust, because we can learn from other ecosystems too, especially from C++. A lot of benchmarks. There is a very, very big article that covers a lot of topics, so highly recommend to read. And only after that, please read Rustc PGO documentation. Highly recommend LLVM Discord, if a dedicated channel about optimization and so on. The people is very responsive. And my contacts. And that's it for today. I hope you will integrate PGO into your application. Thank you.
Thank you, Alex. We can take one question. Anybody? I'm going to go with James, because Simon, you've asked lots of questions. They're great questions, but.
Thank you. So I'm curious, there's obviously a workflow that you need to implement for this. How does it compare to cases that I've seen in say, the Intel compiler, where you can define statically, this is a hot path, or this is the number of loop iterations we expect in this place?
Actually, I had a couple of requests for doing so. I'm a human, and by design, I'm a lazy one. So I don't want to do a thing that the compiler can do for me. And another point that when you codify this like hot, cold branches into your code, it cannot be easily and automatically adapted to another type of workload. So this is a huge advantage for using PGO instead of manual tweaking. And that's it.
All right, thanks, Alex. What's step number 4 before profit? Why are we gatekeeping this? We'll talk later, clearly. Thank you so much, Alex, for your talk and talking about PGO optimization.
Thank you.